We're going to be looking at the AVR ADC PLIB driver, looking at basic mode first using the data streamer, which will help us visualize our ADC samples on a graph and get a better runtime sense of the ADC's performance. Then we're going to be looking at using the accumulator mode to smooth out our results. So this is the application we're going to build in this video. So here we are plotting the ADC result, a number of ADC samples, and toggling a debug GPIO every time a sample is taken. Steady state of our potentiometer represents the noise that we'll attempt to remove in the second part of this video. So here we are building on some fairly fundamental use cases with the timer and the data streamer. So the data streamer use case, sending frames at a period set by the timer, in turn builds on the 100 millisecond timer use case. So if this feels too fast, have a look at timer counter A or the data streamer for those use cases. We're going to start by adding three components: the ADC, data streamer, and timer counter A. My starting point is an empty MCC Melody project for the AVR 128DB48. So starting with the data streamer, then a timer, TCA0, and scrolling up to the top and finding an ADC. Okay, so the ADC, the important thing first of all is that the ADC clock is not more than 2 megahertz. We can find this out by checking the electrical characteristics and seeing that the minimum clock period is 500 microseconds or 2 megahertz. We don't want left adjust. That's mainly useful to use the ADC result high register as an 8-bit ADC result. The ADC is closely associated with the voltage reference, which supplies all the analog peripherals. Here we see the ADC, DAC, and analog comparator. So I happen to be using a pot3 click, and there is a surface mount resistor which selects a voltage reference. So the 2 volts, which is what is mounted on my board, gives us a maximum output voltage of 2.048 volts. Note that some AVRs may have the voltage reference as part of the ADC hardware settings. For now, I'm going to select VDD as voltage reference. Now onto the data streamer. So we'll select a UART dependency, and we'll have 2 variables, ADC result and ADC sample count. Note we have a warning to select a UART dependency. So here we can see that UART 3, PB0 and 1. So UART 3, the warning goes away, PB0 and 1. ADC result is a 16-bit UINT 16, and our ADC sample count will be a UINT 8. We needed a 100 millisecond timer, which means we changed the prescaler high enough so that we can get the 0.1 that we're wanting. That'll do it. So we now enable overflow interrupt, which gives us a warning that global interrupts need to be enabled. So under interrupt manager, we enable the global interrupt and the warning goes away. Now onto the pins. So we look at the hardware users guide, and here we look for the Curiosity Nano base for clicks, and I happen to have a potentiometer connected in microbus slot 1, so that's the analog pin there, PD4, which is our analog input 4. Pin grid view, port D4, and under pins, here you can select digital input buffer disabled. So this makes it a purely analog pin. We checked the UART pin already. For the LED pin, select as output and name it LED. So that was PB3. We name that LED. Right, configuration done. Generate code and look to add these code snippets into main. The include is the same as default, so we can copy this whole code snippet and just replace what's there. So we have a timer interface and a description of what is happening there. We'll also copy the timer callback and the main code snippets. So here we have access through the timer interface to various basic functions of the timer. Here we've defined a callback. That's the timer callback 100 milliseconds. And the point to watch out for is this analog input 4. This code happens to match my hardware setup, but you will select a different analog input here depending on your schematic. So we set the result to the data streamer ADC result and increment the sample count. We then toggle a LED, which is also a debug GPIO, set our send frame flag to true, which we then send a frame in the main while loop. So let's program the board. Programming complete. We can open the data visualizer. Here we can select new variable streamer and import. Here we navigate in MCC generated files, data streamer for the DS file, and click next. And then imports those variables. So we can see some basic activity here. Let's add our debug GPIO. Debug GPIO 1 is our LED, and we start this running. Okay. So this is accurately representing my potentiometer value. I let the samples settle near the bottom of the plot, and here I can see that the noise is between 64 and 66, so about 2 bits of noise. So now if we go back to our ADC and select accumulation and 64, so we can generate now. Scroll down, you can see that there's one extra line of code here to do some bit shifting. You may notice we're only bit shifting 4 for 64 samples. This is because the least significant bits of the result are truncated to fit in the register size. Okay, so we can program this board now. Okay, and you can see after the board has been programmed, a lot of the noise has gone away. So we have a much smoother signal. Or at least here you can see we are down to a single bit.